Nanomaterials have extremely small size, which having at least one dimension 100 nanometers or less. Common types of nanomaterials include nanotubes, dendrimers, quantum dots and fullerenes. Nanomaterials have applications in the field of nanotechnology, and displays different physical-chemical characteristics from normal chemicals such as silver nanoparticles, carbon nanotube, fullerene, photocatalyst, carbon nano, silica, and so on. According to Siegel, nanostructured materials are classified as zero-dimensional, one-dimensional, two-dimensional, three-dimensional nanostructures. Nanomaterials are materials which are characterized by an ultrafine grain size less than 50 nanometers or by a dimensionality limited to 50 nanometers. Nanomaterials can be created with various modulation dimensionalities as defined by Richard W. Siegel, 0 such as atomic clusters, filaments and cluster assemblies, 1 such as nanolayers, 2 such as ultrafine grained overlayers or buried layer, and 3 such as nanophase materials consisting of equiax nanometer-sized grains. For example, quantum dots with size of few nanometers can be considered as a zero-dimensional nanomaterial. Carbon nanotubes can be considered as an one-dimensional nanomaterial. Graphene or nanoplate can be considered as two-dimensional nanomaterials. Nanocubes with unit size of 50 nanometers can be considered three-dimensional nanomaterial. These materials have created a high interest in recent years by virtue of their unusual mechanical, electrical, optical and magnetic properties. First, nanophase ceramics are of particular interest because they are more ductile at elevated temperatures as compared to the coarse-grained ceramics. Second, nanostructured semiconductors are known to show various nonlinear optical properties. Semiconductor quantum particles also show quantum confinement effects which may lead to special properties, like the luminescence in silicon powders and silicon germanium quantum dots as infrared optoelectronic devices. Nanostructured semiconductors are used as window layers in solar cells. Third, nano-sized metallic powders have been used for the production of gas-tight materials, dense parts and porous coatings. Cold welding properties combined with the ductility make them suitable for metal-metal bonding, especially in the electronic industry. Fourth, single nano-sized magnetic particles are monodomains, and one expects that also in magnetic nanophase materials the grains correspond with domains, while boundaries on the contrary to disordered walls. Very small particles have special atomic structures with discrete electronic states, which give rise to special properties in addition to the superpramagnetism behavior. Magnetic nanocomposites have been used for mechanical force transfer such as ferrofluids, for high-density information storage and magnetic refrigeration. Fifth, nanostructured metal clusters and colloids of mono or plurimetallic composition have a special impact in catalytic applications. They may serve as precursors for a new type of heterogeneous catalysts, cortex catalysts, and have been shown to offer substantial advantages concerning activity, selectivity and lifetime in chemical transformations and electrocatalysis, fuel cells. Enantioselective catalysis was also achieved using chiral modifiers on the surface of nanoscale metal particles. Sixth, nanostructured metal oxide thin films are receiving a growing attention for the realization of gas sensors such as nitrogen oxide, carbon mono or dioxide, methane, and aromatic hydrocarbons with enhanced sensitivity and selectivity. Nanostructured metal oxide such as manganese oxide finds application for rechargeable batteries for cars or consumer goods. Nanocrystalline silicon films for highly transparent contacts in thin film solar cell and nanostructured titanium oxide porous films for its high transmission and significant surface area enhancement leading to strong absorption in dye-sensitized solar cells. Finally, polymer-based composites with a high content of inorganic particles leading to a high dielectric constant are interesting materials for photonic bandgap structure. Now we are ready to explore a variety of nanomaterials. First of all, I would like to introduce semiconductor nanomaterials and quantum dots to you. I believe that many of you have already heard about the quantum dots. Actually, some of you might have used quantum dots for display materials or catalytic materials. Basically, quantum dots are semiconductor nanomaterials with electronic band gap. If the quantum dots absorb external energy which is greater than the band gap, electron in the valence band can jump to the conduction band. The detailed electronic band structures of the conduction level is determined by the electron density, nucleus size, and electron affinity of the atom. For example, in the right figure, you can find the simplified schematically illustrated electronic structures of the quantum dots. Once the electrons jump to the conduction band, they are thermodynamically unstable and prone to the transition from the conduction to valence band. In the course of the transition, some of the electrons suffer energy loss by phonon vibration which turn the vibration into heat. When the electrons finally suffers transition from the conduction band which is the excited state to the valence band which is the bottom state, the energy loss is converted into photons. This is called as fluorescence. Some the electrons suffer further interstate transition in the conduction band, and energy loss by the phonon vibration or defects such as disclination, dislocation or other topological sink or add atoms. Finally, the electrons suffer interband transition, from which the energy loss is converted into photon, which is called phosphorescence. By the photoluminescence of quantum dots, we basically mean the fluorescence from the electrons' interband transition. In the left figure, you can find the various processes with input and output energy intervened by the quantum dots. For example, quantum dots can absorb ultraviolet light directly or indirectly with luminophore, and then turn the absorbed photon energy into visible photons. Quantum dots can directly absorb external electrons and output electrons, which can be turned into photocurrent. Basically, we can understand the size-dependent bandgap of the quantum dots using quantum mechanics. I believe that many of you have already taken introductory quantum mechanics of chemistry. In the course, I think you solved a famous practice problems for the energy quantization, such as 1, 2, or 3-dimensional particles in a box or confined potential problems. You can use this model to understand the size dependency of the quantum dots. As you can see the quantized energy as shown in the lower left equation. The allowed bandgap energy increases with decreasing the size of the quantum dots. This means that you can control the absorption energy from ultraviolet to near-infrared, not to mention of the entire spectrum of visible light. For example, cadmium selenide quantum dots with size from 2 to 6.5 nanometers can cover the entire visible spectrum as shown in this color figures. Due to the properties of broadband absorption of quantum dots, they can be good light source with sharp emission with 20-30 nanometers peak width. However, single quantum dots have severe problem which is relatively low quantum efficiency. The quantum efficiency or quantum yield is the ratio between the absorbed energy and the energy of the luminescent photons. For example, cadmium selenide quantum dots have 5% quantum yield. This is due mainly to the high concentration of defects such as trap states. To overcome the low quantum efficiency, researchers have developed core shell structure in which core and shell have different electronic structures. For the higher quantum efficiency, the two electronic states can be matched to minimize diffusion barrier, defects concentration, and scattering of electrons at the core shell interface. This makes the quantum efficiency notably high. For example, zinc sulfide core and cadmium selenide shell quantum dots show quantum efficiency higher than 50%. For the good shell materials, it is important to select higher bandgap semiconductor than the core semiconductors. And it is also important to select the shell to work as a passivation layer for the core. To make the quantum dots solution, we can modify the surface of the quantum dots using hydrophilic polymer coating and quantum dot bioconjugation. One of the conventional problems of the quantum dots is its photo-blinking. The photo-blinking is a phenomenon in which the generation of fluorescent photons is not synchronized with the on-off frequency of the external photon supply. This is not good for applications such as display materials, which requires short response and decay times of the luminescence. To overcome this problem, multi-component core shell quantum dots can be used to minimize response time and decay times. For example, one can use 4-component 4 visible light quantum dots as shown in the right figure. We can modify the crystal structures or shapes of quantum dots to enhance quantum efficiency and suppress photo-blinking. As shown in the lower right figure, pyramidal-shaped quantum dots exhibit very narrow peak width for the fluorescence as well as suppressed blinking. It is also possible to use mixture of the multi-components without the core shell structures. Due to chemical potential gradient, it is possible to drive the microphase separation in the quantum dots, in which large bandgap materials can be driven to form the shell-like structure. However, every component are distributed over the quantum dots. Another way is to use silica sheath and metallic nanoparticles on the sheath. As shown in the left figure, this configuration show good quantum efficiency and suppressed photoblinking. One of the semiconductor nanomaterials I would like introduce to you is zeolite. Zeolites are hydrated aluminosilicate minerals made from interlinked tetrahedra of alumina and silica. In simpler words, they're solids with a relatively open, three-dimensional crystal structure built from the elements aluminum, oxygen, and silicon, with alkali or alkaline earth metals such as sodium, potassium, and magnesium plus water molecules trapped in the gaps between them. Zeolites are very stable solids that resist the kinds of environmental conditions that challenge many other materials. High temperatures don't bother them because they have relatively high melting points over 1000 degrees Celsius, and they don't burn. They also resist high pressures, don't dissolve in water or other inorganic solvents, and don't oxidize in the air. They are not believed to cause health problems through, for example, skin contact or inhalation, though in fibrous form, they may have carcinogenic, cancer-causing effects. Since they're unreactive and based on naturally occurring minerals, they're not believed to have any harmful environmental impacts. Although zeolites might sound incredibly boring, their stable and unreactive nature isn't what makes them useful. The most interesting thing about zeolites is their open, cage-like, framework structure and the way it can trap other molecules inside it. This is how water molecules and alkali or alkaline earth metal ions, positively charged atoms with too few electrons, sometimes called cations, become a part of zeolite crystals, although they don't necessarily remain there permanently. Zeolites can exchange other positively charged ions for the metal ions originally trapped inside them and, as Kronstedt found over 250 years ago, they can gain or lose their water molecules very easily too. Zeolites have regular openings in them of fixed size, which let small molecules pass straight through but trap larger ones. That's why they're sometimes referred to as molecular sieves. Unlike natural zeolites, which occur in random forms and mixed sizes, synthetic zeolites are manufactured in very precise and uniform sizes, typically from about 1 micrometer to 1 millimeter to suit a particular application. In other words, they're made a certain size to trap molecules of a certain smaller size inside them. Although all zeolites are aluminosilicates, some contain more alumina, while others contain more silica. Alumina-rich zeolites are attracted to polar molecules such as water, while silica-rich zeolites work better with nonpolar molecules. The cage-like structure of zeolites makes them useful in all sorts of ways. One of the biggest everyday uses for zeolites is in water softeners and water filters. In ion exchange water softeners, for example, hard water, rich in calcium and magnesium ions, is piped through a column filled with sodium-containing zeolites. The zeolites trap the calcium and magnesium ions and release sodium ions in their place, so the water becomes softer but richer in sodium. Many everyday laundry and dishwasher detergents contain zeolites to remove calcium and magnesium and soften water so they work more effectively. Zeolites form with many different crystalline structures, which have large open pores in a very regular arrangement and roughly the same size as small molecules. There are about 40 naturally occurring zeolites, forming in both volcanic and sedimentary rocks. According to the U.S. Geological Survey, the most commonly mined forms include chabazite, clinoptilolite, and mordanite. Zeolites are typically synthesized using silica or alumina building blocks. Depending on the growth conditions, the blocks can be assembled into sodalite or pentosyl unit. And the units are further assembled to form nanoporous structures. Dozens more artificial, synthetic zeolites, around 150, have been designed for specific purposes, the best known of which are zeolite A for laundry detergent, zeolites X and Y for catalytic cracking, and the petroleum catalyst pentosyl zeolite. Due to high surface-to-volume ratio, and size or shape selectivity of single molecule or molecular clusters, various zeolites can be used to control the chemical reaction. When incorporated with noble metals inside, zeolite is turned into advanced catalyst. For example, as shown in the right figure, palladium-nickel or palladium-cobalt clusters on the zeolite can turn the aldehyde into hydrogen and carbon dioxide gases. This is promising in the production of hydrogen for fuel cells. Second, let us meet the metallic nanoparticles. They have wide range of applications, from imaging agents, catalysts for chemical reactions, therapeutic applications, diagnostic application for healthcare, sensors, and so on. As was shown in the case of semiconductor nanoparticles, it is also possible to control the size and shape of the metallic nanoparticles. By tuning the size and shape, their resonance properties with given wavelength of light can be varied, which generate different colors as shown in the rightmost figure. One of the notable differences of the metallic nanoparticles from quantum dots is that the optical and electronic properties of the particles can also be controlled by the shape as well as size of the particles. For example, polytope or polygon-like particles with triangular, tetragonal, or hexagonal shapes exhibit different resonance wavelength than spherical particles of the same size. The shape-driven properties of the metal nanoparticles are due mainly to the multipolar interaction of localized surface plasmon around the metal nanoparticles. Interestingly, it is also possible to use multi-components metal to form high-entropy alloy nanoparticles as shown in the lower right figure. The multi-components metallic nanoparticles can work for the advanced catalyst for chemical reaction. The most notable physical property of the metal nanoparticles would be photonic or optical property. The peculiarity in the property relies on the negative value of the imaginary part of the dielectric constant of metallic nanoparticles. Metal has a good electrical conductivity, which results from the free electrons around the nucleus of the metal atoms. The free electrons around the metal nanoparticles can respond to the external electromagnetic wave. In particular, the electrons can move in opposite direction of the vibration of the applied electric field of the electromagnetic wave. There exists intrinsic vibrational frequency of the electrons of the metal nanoparticles, and if the frequency of the externally applied electromagnetic wave can provide resonance for this intrinsic frequency, the electrons and photons can move like a unified particle, which is called plasmon. The plasmon is formed near the surface of the metal. For nanoscale metallic structures, the plasmons are localized near the particles, which is called localized surface plasmon resonance. The resonance frequency is a function of the size and shape of the particles, which provide tunability of the photonic and optical properties of the metal nanoparticles as shown in the lower left plots. In particular, the tunability in the visible spectrum is useful for the optical sensors, display materials, solar cells, photodetectors, and so on. Another important property of the metal nanoparticles or nanostructures is surface-enhanced Raman scattering. As shown in the right figure, when the incident light in the experiment strikes the surface, localized surface plasmons are excited. The field enhancement is greatest when the plasmon frequency is in resonance with the radiation. In order for scattering to occur, the plasmon oscillations must be perpendicular to the surface. If they are in plane with the surface, no scattering will occur. The light incident on the surface can excite a variety of phenomena in the surface. Yet the complexity of this situation can be minimized by surfaces with features much smaller than the wavelength of the light, as only the dipolar contribution will be recognized by the system. Molecules can interact with externally applied electromagnetic wave. During the interaction, there is an exchange of energy and a change in the light's direction which appears as scattered light from the molecules. This scattering is inelastic scattering, and therefore, can reveals the chemical composition and molecular structures. This scattering is called Raman scattering. Visible and near-infrared radiation are used to excite Raman modes. When certain molecules are on the metal nanostructures, Raman scattering is greatly enhanced at the surface due to the same mechanism that excited the incident light, resulting in a greater increase in the total output. Even when an excited molecule is relatively far apart from the surface, metallic nanoparticles can induce surface plasmon phenomena. The enhancement is not equal for all frequencies, and therefore, resonance peak can work as a fingerprint to identify the molecule. The choice of surface metal is also dictated by the plasmon resonance frequency. Silver and gold are typical metals for the surface-enhanced Raman scattering because their plasmon resonance frequencies fall within these wavelength ranges, providing maximal enhancement for visible and near-infrared light. Among various nanomaterials, the most famous nanomaterials would be carbon-based nanomaterials. Carbon is the lightest atom in the fourth column of the periodic table and is an element with unique and significant properties. It can bind itself or to other light atoms, giving rise to organic chemistry and therefore to biochemistry and the miracle of life on Earth. Carbon-based materials are unique in several ways. Carbon forms a wide variety of allotropic forms like graphite, diamond, etc. We are already familiar with different forms of carbon such as diamond, which is carbon materials purely composed of sp3 molecular hybrid orbital. At the tip of a pencil, you can find graphite, which is a multi-layered stacking of thin carbon sheets. In charcoal, you can find three-dimensional carbon materials, which is amorphous carbon black. This material is a mixture of sp2 and sp3 hybrid molecular orbitals. As was explained in Lecture 1, the first carbon nanomaterial fullerene had already been developed in the 1980s. In 1990s, Japanese chemist Sumio Ijima synthesized single and multi-wall carbon nanotubes, and in 2000s, two-dimensional carbon nanomaterial graphene was synthesized. Therefore, fullerene, carbon nanotubes, and graphene are synthetic carbon nanomaterials. Interestingly, there are few undiscovered carbon nanomaterials such as diamondine, which is three-dimensional ordered net with a mixture of sp3 and sp molecular hybrid orbitals. Another predicted form of carbon nanomaterial is graphene, which is two-dimensional carbon nanomaterial. Actually, it is different from graphene, in that graphene is a mixture of sp and sp2 hybrid molecular orbitals, while graphene is composed of purely sp2 hybrid molecular orbital. Actually, there are various different shapes of carbon nanomaterials, which are called as carbon allotropes as shown in the right figure. Very interestingly, these carbon allotropes have very different physico-chemical properties such as electrical, optical, plasmonic, catalytic, chemical, surface, and photonic properties. They can work as a filler or substrate for preparation of advanced materials such as lightweight ultra-strong composite materials, substrate for the two-dimensional inorganic nanomaterials, guiding substrate to grow polymeric thin films, and so on. The most famous carbonaceous nanomaterials would be carbon nanotubes. In 1991, Sumio Ijima presented transmission electron microscopy observations of elongated and concentric layered microtubules made of carbon atoms. This propelled the research related to one of the most actively investigated structures of the last century, nowadays called the carbon nanotubes. Following Ijima's groundbreaking discovery of multi-wall carbon nanotubes, carbon nanostructures, and in particular carbon nanotubes, have been at the forefront of scientific research in physics, chemistry, materials science, and so on. The discovery of single-wall carbon nanotubes in 1993 set yet another milestone in an exponentially growing field. Conceptually, these new nanoforms of carbon allotropes with cylindrical geometry belong to the versatile family of fullerenes. Fullerenes were discovered by Harry Crito, Robert Curl and Richard Smalley in 1985. This nanometer scale structure was named fullerene due to its resemblance to the highly symmetric domes designed by the architect Richard Buckminster Fuller. Buckminster fullerenes or fullerenes are the third allotrope of carbon and consist of a family of spheroidal or cylindrical molecules with all the carbon atoms sp2 hybridized. C60 was the first fullerene to be discovered. Called the buckyball, it is a soccer ball-shaped molecule with 60 carbon atoms bonded together in pentagons and hexagons. The carbon atoms are sp2 hybridized, but unlike graphite, they are not arranged in a plane and is made up of 12 pentagons and 20 hexagons arranged in a spherical shape. The tubular form of the fullerenes are called carbon nanotubes. Carbon nanotubes have attracted a lot of researchers in a wide range of fields from academia to industry, not only because of their uniqueness when compared with conventional materials, but also because they are very promising materials in nanotechnology. Actually, there is a chemical complex for mass production of carbon nanotubes in South Korea and China. A carbon nanotube is a tube-shaped material, made of carbon, having a diameter measuring on the nanometer scale. To understand the structure of a carbon nanotube, it can be first imagined as a rolled-up sheet of graphene, which is a planar hexagonal arrangement of carbon atoms distributed in a honeycomb lattice. A single layer of graphite sheet is called graphene. Carbon nanotubes have many structures, differing in length, thickness, and in the type of helicity and number of layers. As a group, carbon nanotubes typically have diameters ranging from 1 angstrom up to 50 nanometers. Their lengths are usually several microns, but recent advancements have made the nanotubes much longer, and measured in centimeters. Here are two types of carbon nanotubes. Firstly, single-wall nanotubes are tubes of graphite that are normally capped at the ends. They have a single cylindrical wall. The structure of a single-wall CNT can be visualized as a layer of graphite, a single atom thick, called graphene, which is rolled into a seamless cylinder. Most single-wall CNT typically have a diameter of close to 1 nanometer. The tube length, however, can be many thousands of times longer. Single-wall CNT are more pliable yet harder to make than multi-wall CNT. They can be twisted, flattened, and bent into small circles or around sharp bends without breaking. Secondly, there are two structural models of multi-wall nanotubes. Like in the Russian doll model, a carbon nanotube contains another nanotube inside it such that the inner nanotube has a smaller diameter than the outer nanotube. In the parchment model, a single graphene sheet is rolled around itself multiple times, resembling a rolled-up scroll of paper. The simplest representative of a multi-wall CNT is a double-walled carbon nanotube. Multi-wall carbon nanotubes have similar properties to single-wall nanotubes, yet the outer walls on multi-wall nanotubes can protect the inner carbon nanotubes from chemical interactions with outside materials. Multi-wall nanotubes also have a higher tensile strength than single-wall nanotubes. The diameters of multi-wall nanotubes are typically in the range of 5 to 50 nanometers. The interlayer distance in multi-wall nanotubes is close to the distance between graphene layers in graphite, around 3.39 angstrom. Multi-wall nanotubes are easier to produce than single-wall nanotube. However, the structure of multi-wall nanotube is less well understood because of its greater complexity and variety. Regions of structural imperfection may diminish its desirable material properties. Single-wall CNT has an interesting physical property. As shown in this two-dimensional honeycomb-shaped carbon lattice, single-wall CNT can have different chirality. The difference in the chirality leads the electronic structure of the single-wall CNT to be modified. The different electronic structures indicates the different electronic properties and optical properties. For example, for armchair structure, single-wall CNT is metallic, in which conduction band and valence band are overlapped, and charge carrier suffers little electrical resistance. In contrast, the zigzag structure, single-wall CNT is semiconductor, in which conduction band and valence band are not overlapped. Therefore, it forms an electronic band gap. The band gap can be controlled by chemical doping or external field. This property makes the semiconductor single-wall CNT work as the next-generation semiconductor for electronic circuits. By varying the chirality of the single-wall CNT, we can control the properties of the semiconductor, such as tuning the band gap. This is promising properties for the single-wall CNT, since it can be used for structure-based logic circuit at nanoscale as shown in the lower right figure. Okay. Now let us learn about two-dimensional carbonaceous nanomaterial. Graphene is an allotrope of carbon in the form of a single layer of atoms in a two-dimensional hexagonal lattice in which one atom forms each vertex. More specifically, graphene is an one-atom-thick planar sheet of sp2 bonded carbon atoms that are densely packed in a honeycomb crystal lattice. It can be viewed as an atomic-scale chicken wire made of carbon atoms and their bonds. It is the basic structural element of other allotropes, including graphite, charcoal, carbon nanotubes and fullerenes. It can also be considered as an indefinitely large aromatic molecule, the ultimate case of the family of flat polycyclic aromatic hydrocarbons. Graphene has a special set of properties which set it apart from other allotropes of carbon. In relation to its thickness, it is about 100 times stronger than the strongest steel. Yet its density is dramatically lower than any steel, with a surface mass of 0.763 mg per square meter. It conducts heat and electricity very efficiently and is nearly transparent. 3. Graphene also shows a large and nonlinear diamagnetism, 4, even greater than graphite, and can be levitated by neodymium iron boron magnets. Researchers have identified the bipolar transistor effect, ballistic transport of charges and large quantum oscillations in the material. Scientists have theorized about graphene for decades. It has likely been unknowingly produced in small quantities for centuries, through the use of pencils and other similar applications of graphite. It was originally observed in electron microscopes in 1962, but only studied while supported on metal surfaces. The material was later rediscovered, isolated and characterized in 2004 by Andrei Gm and Konstantin Novoselov at the University of Manchester. Research was informed by existing theoretical descriptions of its composition, structure and properties. High-quality graphene proved to be surprisingly easy to isolate, making more research possible. This work resulted in the two winning the Nobel Prize in Physics in 2010. Graphene is a zero-gap semiconductor, because its conduction and valence bands meet at the Dirac points as shown in the middle figure. The Dirac points are 6 locations in momentum space, on the edge of the Brillouin zone, divided into 2 non-equivalent sets of 3 points. The 2 sets are labeled K and K'. This makes graphene have very high electrical conductivity, much higher than noble metals. Due to the property of the Dirac cone electronic structures, effective mass of the electrons or holes is 0, which makes electron moves just like photon, and therefore, electron in the graphene can move with light speed ideally. Although it has metallic electronic structure, it absorbs visible light only by 2.3%, which makes graphene be transparent in visible spectrum. By contrast, For traditional semiconductors, the primary point of interest is generally gamma, where momentum is zero. Four electronic properties separate it from other condensed matter systems. However, if the in-plane direction is no longer infinite, but confined, its electronic structure would change. They are referred to as graphene nanoribbons. If it is zigzag, the band gap would still be zero. If it is armchair, the band gap would be non-zero as shown in the simulation results in the lower pictures. Typically, graphene shares many of its physical properties with CNTs. For example, both carbonaceous materials exhibit much higher electrical conductivity, thermal conductivity, Young's modulus than silicon. Actually, graphene is the strongest materials and thinnest material ever known. Therefore, both materials can be used for the filters to enhance electrical, thermal, and mechanical properties for polymer-based composite materials. One of the most profound mechanical properties of graphene is its ductility. Notwithstanding the high Young's modulus, graphene can be stretchable up to 20%. This makes graphene as potential materials for the flexible electronics. Graphene is also a perfect thermal conductor. This is due to a fact that the thermal transport in graphene is done in mainly ballistic manner. Graphene is the most reactive form among all the carbon allotropes. This reactivity is partially attributed by the large fraction of edge carbon atoms which are typically thermodynamically unstable than the carbon atoms in the honeycomb lattice. It makes graphene easily suffer oxidation at relatively low temperatures such that 350 degrees Celsius. Graphene can be modified with oxygen and nitrogen.